Welcome, everyone. Have you ever felt like math is just, well, an endless, boring stream of crunching numbers on a page? If so, we're going to totally flip that idea on its head today. Math is actually the ultimate tool. Think of it like a massive telescope for understanding the absolutely mind-bending scales of our universe. Today, we're bringing you an explainer of Chapter 2, Power Play. We're going to explore how exponential growth shapes literally everything, from a flimsy sheet of paper right out to the distant planets in our solar system. So, let's dive right in and unlock the real power of numbers.
Here's our roadmap for today's explainer. We'll kick things off with the paper folding paradox, and then move on to the rules of power. After that, we're mapping the universe, before we zoom right back down to Earth for cracking the code. Finally, we'll wrap the whole thing up with the Power Play takeaway.
Section 1. The paper folding paradox.
Our source text kicks things off with this really fun, brain-teasing misconception about how things grow. It's something that completely defies human intuition. Okay, I want you to imagine taking a sheet of paper. Picture the biggest sheet you can find, maybe a huge newspaper or even tissue paper. Now fold it in half once, then fold it again and again. You've probably heard that old myth, right? The one that says you literally can't fold a piece of paper more than 7 times? Well, just for a moment, let's toss physical limitations completely out the window. Let's say you have a super thin sheet of paper just 0.001 centimeters thick. What if you could magically fold it 46 times? What do you think the resulting thickness would be? Take a wild guess.
If you look at the progression here, the sheer speed of it is wild. We start super small. After that very first fold, the thickness is a tiny 0.002 centimeters. But here's the catch. Notice the pattern. It's multiplicative growth. The thickness is doubling every single time. By fold 10, it's just over 1 centimeter. Not too crazy, right? But keep going. By fold 17, that tiny fraction of a centimeter has absolutely exploded to about 131 centimeters. That's over 4 feet thick. See, our brains are super used to additive growth, where things just inch up step by step. But doubling, that scales up aggressively.
And here is the truly shocking truth. If you could keep up that doubling pattern and actually fold that paper 46 times, it wouldn't just be the height of a skyscraper or even Mount Everest. It would literally be thick enough to bridge the entire distance from the Earth all the way to the Moon. I mean, no way, right? But that is the visceral, staggering reality of exponential growth. It starts out so slow and unnoticeable, and then boom, it suddenly explodes into cosmic proportions.
Section 2. The rules of power. Okay, so it's time to transition from the visceral shock of that paper to the moon example and look under the hood a bit. We really need to understand the actual mechanics of how this math works to create such massive numbers. In the expression n raised to the power of a, n is our base. That is the number being multiplied. The a is the exponent. That tiny little number hovering up at the top tells the base exactly how many times it needs to multiply by itself. So if we take the example of 5 raised to the 4th power, it's not 5 times 4. Nope. It's 5 times 5 times 5 times 5. And that gives us 625. Basically, the base sets the foundation, but the exponent, that is the engine of the growth. To help us master these mechanics, we've got a fantastic scholarly OWL guide to show us the ropes. We're going to follow our guide right now to learn the core moves, or you can think of them as the mathematical rules of the game for manipulating these incredibly powerful numbers.
And here is your essential toolkit, the laws of exponents. When you're multiplying two powers that have the exact same base, you just add the exponents together. Easy enough. For a power of a power, you actually multiply the exponents. When you're dividing, you do the opposite and subtract the exponents. And finally, a negative exponent, well, that doesn't actually mean a negative number. What it does is flip the base into a fraction, meaning it becomes 1 over the base raised to that power. These rules are just incredibly elegant. They let us take massive, unwieldy calculations and simplify the whole shebang into basic addition and subtraction of those tiny numbers at the top.
Section 3. Mapping the universe. So now that we have our toolkit sorted, let's apply these rules to literal cosmic scales. Let's test out our newfound skills on the solar system itself. Take a look at the top number there, 70,004,000,000. Written out in standard form, it's super clunky, it takes up a ton of space, and frankly, it's way too easy to miscount those zeros and make a massive mistake. But check out the scientific notation, or standard form, right below it. 7.004 times 10 to the power of 10. It's clean, it's elegant. By using a base of 10 and an exponent, we can pack all of that massive scale into a neat, easily readable package.
Let's see how this builds our understanding of space. Here we're comparing distances from the sun. The Earth is 1.496 times 10 to the 11th power meters away. Now look at Saturn, 1.4335 times 10 to the 12th power meters. Because we're using exponents, you don't have to sit there counting zeros to see the difference. You instantly see that Saturn's distance has an exponent of 12 compared to Earth's 11. That tells us right off the bat that Saturn is a whole order of magnitude further out. Exponents literally let us grasp these terrifyingly massive planetary gaps in a single glance.
Section 4. Cracking the code.
Let's zoom back in from the cosmos to something a little bit more relatable: digital security. Our scholarly guide is back with a very practical problem for us. Think about a digital locker, or maybe even your smartphone, that uses a 5-character alphanumeric passcode. That just means it can use both letters and numbers. Have you ever wondered just how secure that really is? Like, how many possible combinations could there actually be? Let's break it down together.
Here's the step-by-step logic of combinatorial growth. Step 1, we have to find our base. We've got 26 letters in the alphabet and 10 digits from 0 to 9. Add those up, and that gives us a pool of 36 possible characters. Step 2, we identify the length of the passcode. There are 5 slots we need to fill. That's our exponent. So, for step 3, the calculation is 36 options for the first slot, times 36 for the second, times 36 for the third, and so on. Mathematically, that is simply 36 to the 5th power. And guys, when you actually calculate 36 to the 5th power, you get over 60 million possible combinations. It's wild to think that a tiny 5-slot passcode is secured by this massive, invisible wall of multiplicative growth.
Section 5. The Power Play Takeaway. This quote right here perfectly summarizes the journey we've been on today. Rapid exponential growth, also called multiplicative growth, can be compared to additive growth. When we add, we're taking slow, steady little steps. 1 plus 1 plus 1. But when we multiply, when we use exponents, we are jumping. And those jumps, they get wider and faster with every single step. Multiplicative growth creates these incredible explosions of scale that addition simply cannot match. Whether that's folding a piece of paper to the moon, measuring the vast distance to Saturn, or locking down your personal data. Which leaves us with this final thought. We've seen how exponents map the solar system and how they secure our daily devices. But the thing is, exponential growth is everywhere. Think about how fast computer processing power advances, how a virus spreads through a population, or even how a simple social media post goes viral. So, I want to ask you, what else in your world is growing exponentially right now? Keep your eyes peeled for those hidden multipliers in your everyday life. Thank you so much for joining me for this explainer. Keep learning and definitely keep asking questions.